This is our lab we're going to do on AND gates and OR gates. And we're going to use two input gates. Remember, an AND gate and OR gate has got to have a minimum of two inputs, right? The more inputs we have, the more complicated our truth table becomes. So this is why all these are only going to be on two input gates. And we're going to use a 74 LS08. That's going to be our AND gate, and we're going to use a 74 LS32 for our OR gate. And these are quad two inputs. Does that make sense? So they're in 14-pin dips. So that means we have 12 pins to work with, right? You understand? Why do we have 12 pins even though there's 14 pins there? Power, right? Yeah. These are TTL gates, so they run off of 5 volts. TTL signal generator, we've got that on our trainer. So this is going to be this clock output right here. This is the one at the very top. It's labeled clock. So don't use the one called a generator. Generator is an AC output. Clock is a TTL output, which means it's going to be going from 0 volts up to 5 volts. Okay. And then, of course, we'll have to reference it to the common of the trainer, which is this black one on the very bottom. Okay. And we'll look at a little bit more of that in a little while. I'll have to look and see if we actually need a 1K ohm resistor. We might not need that. And of course, 5 volt supply. 5 volt supply is on the trainer. This is the discussion section that you probably need to read. This gives us a truth table. This is telling us a way that we can expand our gates. So even though these are two input OR gates, we could come in and there's 4 of them in there, right? You understand that? So what that means is I might only need one OR gate. I might need one 2 input OR gate, and then I might need one 4 input OR gate. Does that make sense? Well, what we can do is we know we got one with 2 inputs. Now, how are we going to get to one with 4? Well, a lot of people think they would have to go out and add another integrated circuit, right? Does that make sense? Well, what we can do is we can simulate a 4 input OR gate by using by connecting it like this. Does that make sense? Yes or no? Yeah, well, if this is an OR gate, then what that means is, it means that 2 to that power, right? You understand? So that means we have 16 combinations I could put on a 4 input gate. So if I was going to set up the truth table, and I'm looking for a PowerPoint, guys. I know I have it up here. So that means inside the quad 2 input OR gate, I have 4 gates to work with. I need one of these. Right, you understand? And I need one of these in my circuit that I'm working on. Well, what most people would do is they would buy 2 integrated circuits. One of them that give you the 4 input OR gate. They would find one, and then the other one that use a 2 input OR gate. But now you're going to have 2 14-pin dips that you had to go out and buy, right? You understand? Well, what they're trying to show us is using this circuit right here. This will act like a 4 input OR gate. So if I call my inputs A, B, C, and D, and then I come over here and start a truth table. Now, if this is an OR gate, what do we say about what's the expression for an OR gate? The way we give expressions, all highs get a high, any high. Yeah, this says any high on the input would equal a what? A high on the output. Okay. So I come over here and we can trace this through. We'll call the output X. So right now I come up here and I start off with all zeros. That would be one of my combinations. So we'll go ahead and write the combinations. I know I got 16 of them. And all we have to do, and this is the way the truth table start out, you just start counting in binary. So that'd be 0, that'd be 1, that'd be 2, that'd be 3, that'd be 4, that'd be 5, that'll be 6, that'll be 7. 1, 7, that'll be 8. I'm gonna write a room. 8, that'll be 9. I'm gonna have to move this up to the top, guys. Raise 2 to the number of inputs. So how many inputs do I have here? 4. So 2 raised to the 4th power is 16. Right? You understand that? So that tells me the number of input combinations I'm going to have to come up with on my truth table. And this is where truth tables, this is later on we're going to see that once we get past 4 inputs, then truth tables are going to become even too cumbersome to even use, right? You understand? Because if I went to 5 inputs, then I jump by 2 times 16. So that means if I do just 5 inputs, I got 32 combinations in my truth table. We're going to deal with an 8 input NAND gate. That would be 256 entries in a truth table that all I got to know is all highs equal a low, right? You understand? So learning the expression is more important basically than trying to figure out truth tables, even though we're going to deal with them, but we're going to only deal with nothing more than 4 inputs. I got my, let's try to get them in line. It'd be easier for me to see. That'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I have a tendency to drift, guys. I'm sorry. 14, 15. So there's my 16 inputs. So if I come over here and put all zeros over here, what would I get out? They'd give me a 0, 0, they'd give me a 0, right? So I get a 0 out. I come over and put a 1 right there. That's going to put a 1 right there. That's going to put a 1 on the output, right? And of course, you can see what's going to happen for all these combinations. It's going to be all 1. So we're saying any high would give me a what? A high. So you can see truth tables are good just to make sure you understand how circuits work, right? You understand that. But once you get past 4 inputs, the truth tables are going to be prohibitive. Nancy, they're going to talk about something in a textbook for reducing equations called Karnoff maps. And once you get past 4 inputs, Karnoff maps just become useless because they start getting so big to even do what? Even to fool around with. So this is what they're trying to say. Instead of me going out and buying 2 ICs, right? You understand? I can use a 2 input AND gate, right? You understand? And then I can have a 4 input AND gate. Now that's going to use all the gates in there because that's all 4 of them, right? Does that make sense? But what I've done is, and we're going to look out later on how we can do this with NANDs and NORs. NANDs and NORs are called universal gates. And what that means, you can get every function out of NANDs and NORs. You can wire NANDs to be ANDs, but you're going to have to use multiple gates to get those functions. And we'll look at that. So that's what they're telling you right there in here. It says, okay, and that's what I can find my lab. Where is it? Over here. You're going to do the pin out. Everybody okay on doing pin outs, right? Where you going to get that information at? If you got your textbook, it's going to be in there. If not, then you'll get on Blackboard and you'll open up Blackboard and look at data sheets and you'll find the data sheet. The data sheet will give you the pin out. And what is the pin out of an IC? Yeah, what is it? If I say define pin out, what is define what an IC pin out is? What is an IC pin out?
It's the amount of pins on each.
Well, here's a pin out. I got these little tiny black lines on the right hand side. This is not the pin out. The pin out shows you what is assigned to every pin. That's what the pin out is. The pin out shows you this is a 14 pin DIP. What could that be? Well, that could be NAND gates, that could be OR gates, that could be inverters. So we've got tons of guys that use this 14 pin DIP. It could be a voltage regulator. It could be an adder. It could be a subtractor. It could be almost anything unless I know the pin out. If I don't know the pin out, I don't know how to connect this thing. Does that make sense? So when I go up here to Blackboard, I'm not going to go to Blackboard. I'm not going to take the time to log into Blackboard. But every IC that we use is on the main menu called the data sheets. So we'll go into the data sheets and we'll look up a 74 and a 7408 is one we're using. And look, well, the first things they give you is the what? The pin out. So there's the pin out right there. So I know pin 14 is what? Is power, right? DCC. I know that pin 7 is common, right? You understand that? And then this is going to be one gate right here. This is going to be another. Now, the only thing these gates have in common is they share the same power pins and they're inside the same package. Y'all understand that? DCC and TTL, and we've talked about this already. In digital, in solid state DCC, all we know is that it's what we call a collector voltage, and it can be anything. In digital, VCC is plus 5 volts. Plus and minus a certain percentage. So I can come down here and I can look, and this right here, this is called the recommended operating. VCC can be anywhere between 4.5 volts and 5.25 volts. So it's given a range because it is impossible for me to make sure if I develop power supplies to get every one of them exactly the same, right? Y'all understand that? So what they've done is they've got a range that it's in between there. So if it says if your power supply is anywhere between 4.5 and 5.25, then all of this stuff down here is true. If it's not between that range, then none of this stuff down there is guaranteed anymore. So we'll get into data sheets in chapter 9. In fact, we'll jump ahead into chapter 9 because learning how to read these data sheets are very, very important. All we're really concerned with right now is this pin out that tells us how to do what? How to connect that IC. That makes sense? Yes or no? So that's what we'll do. We go up on the data sheet and we'll do what? We'll come up here and we'll assign these pins. Before we do what? Before we connect the circuit. So you just can't choose a pin to connect to, right? Oops, sorry. I can't remember the lab. I think does does NANDs first. Yeah. So this is the AND. This is 7408. And if you look at the Labasseser, it says, I can't see. Well, each one of them would require how many pins? A 2-input AND gate would require how many pins? Would require how many pins? A 2-input gate AND gate inside an integrated circuit would require how many pins? Huh? 3. Why? 2 inputs and 1 output. Okay, so I got 12 pins to work with, a 14-pin dip. I got 12 pins to work with because we lose one for what? Power, and we lose one for common. Okay, so that means we could get 4 of them in there. And when I look at the pin out, which we know what it means now, right? You understand that? When I look at the pin out, oops, this is the way they're assigned. So AND gate number 1, which they're calling, so they're calling this A1, B1, and Y1. Can y'all see that? So they're calling this, they're numbering this gate 1. And over here they're calling this A2, B2, and Y2. Right? You understand? Okay. So when I come up here and do this pin out, oops, wrong thing. So when I come up here and do this pin out, this is what you're going to do, right? What you're going to do is you're going to look at that pin out, and you're going to come over here and you're going to draw the way these guys are inside here. So this is one of them, right? And then the other one would be where? It would be right here, yeah, of course. And then my other ones will be on this side over here. And this is going to be over here. This is going to be what they call what? A1, good. A2. And then they're calling this Y1. And then this right here would be what? I'm sorry, this would be B1. This would be A2, B2, Y2. Right? Understand? This right here would be common. They call it ground. Like I said, that's one of the most unused terms in electronics, is what common and what ground is. And then what I will do when I come out here and wire this thing, where's my, right here. Of course, the first one was oh, here we go. And what we're going to wire, how we're going to wire this thing is we're going to come up here and just, let me find my drawing. We're going to take the 2 inputs and we're going to hook this up to our data switches on our trainer. Everybody okay? There's actually 5 of them there. This might go back to, it can get, you can use any switch up 2 switches you want to up there. It really don't make any difference. So we could use 7 and 6. And then we're going to take this over here and we're going to run this over to one of our LEDs. And the LED is going to be up here. It's going to be red. Are you okay? Does that make sense? Yes or no? So here's our data switches right here. They run from 0 to 7. Says up is a what? A high, and down is a low. And here's the connection to our LEDs right here. So I should see all highs get a high, right? You understand? So we'll go through 4 combinations because 2 input or AND gate. We'll go through 4 combinations, but you should be able to tell all highs equal high. Right? That makes sense? Now, one thing people forget to do is forget to do what? They forget to power it up. Yeah, they'll come up here and look at this diagram right here, and these diagrams don't show the power, they just show you how, right? You understand that? But it's up to you to understand that these guys don't work unless you hook up the VCC and the common, right? Everybody understand that? Somebody in this class is going to do that. They're going to wire it up. This thing's not working. The output is going to the terminal board that controls the light. There's an integrated circuit in there that controls that LED. It's a light emitting diode. Yeah, so it's a very simple circuit. These labs, the circuits themselves are not that complicated. So we're going to wire it across the trough, right? You understand that, right? And then we're going to bring plus 5 volts in ground and common up to here, right? You understand that. Then we're going to take the inputs and wire them up to what? 2 of these data switches. Which ones? Yeah, any one, right? And we're going to take the output and wire it up to one of these LEDs. Okay. We're not wiring it to the LEDs. We're wiring it to the circuit that controls the LEDs. That makes sense? And then what are you going to do? Then you're going to fill in the truth table, right? And you should expect all highs to get a high. So here's your truth table. It says you're going to go through all of the combinations. We know there's 4 because it's a 2 input, and you're going. So the switches, when they're down, you're getting a 0. When they're up, you're getting a 1. And you should see what? You should see all highs get high. So this should be a 0. This should be a 0. This should be a 0. This better be a 1. A 1. Then we're going to come down here and we're going to go do the same thing, but this is going to be for an OR gate. First thing we're going to do is do what? We're going to do the pin out. Next thing we're going to do, guys, and this is in the lab book, is we're going to write the pin we're going to assign to these ICs. We're going to assign it. You got 4 you can work with. Which one are you going to use? Whichever one you want to. Does that make sense? Right now, whichever one you want to. You got 4, you're only going to use one of them. You got 4 of them in there. You can use whichever one you want to. But what you're going to do is, before you wire up any circuit in this class, is you're going to write your pins over here on your diagram. And then that way I don't have to think about anything when I come over and check it out, right? You understand? Because you've written out the pin out. And if we ever looked at a print of a digital circuit, that's what you're going to see. You're going to see the engineers that drew the thing. I'll show you. Actually, this is actually oh, dang it. I don't know if I've got it or not. I couldn't find it. But if you ever looked at a digital print, oh, here we go. Oops. So you see, one of the first things they do when they design these things is they assign the pin. And you can see this is U47 and this right here, I'm sorry. So normally this is U4, U4A, and U4B. You know what they're doing, but look, this one uses pins 1, 2, and 3. This is the exact same IC, but it's using pins what? 4, 5, and 6. So they get the same U number. So this is very simple. When we assign symbols on a schematic, what they like to do is they like to use one letter. So every once in a while you'll see IC, but most of the time we have letters that are very common. So transistors, they use Q. So that would be silk screened on the circuit board, right? And we'll show y'all some circuit boards. So I would find that. Those are dip switches. It's normal to sign integrated circuits U, because they couldn't use C. C is assigned to capacitors, so they just started using letters of the alphabet. So U is a very common indicator of an integrated circuit. Y'all know what we mean? Yes or no? Yeah, so this is not an extremely good example. So we got to make these things so we can troubleshoot them, right? You understand? So we got all these integrated circuits, so they come up with designators for these different guys. And I've got a schematic. So if I get this to focus in. No, this is not a good example. But see, integrated circuits, they label, so I'm looking at a schematic. Now this guy right here, this is not a good example because they're covering up everything. So I'll find another one to show you. But what they'll do is you got a schematic and you're trying to find this integrated circuit. And you got 50 of them on the circuit board. Well, how are you going to find it? Well, they give it a designator, right? And they print that on the board. So they'll have like U3, and you see U3 and you find U3 on the circuit board, and that's the way you can find it. So two of the things that we do on schematics is we do what? They assign it so C are for capacitors. So if I'm looking for C1, right, you understand, then I just find C1 labeled on the circuit board, right? You understand that? Transistors are U. I'm sorry, transistors are Q, right? You understand? Integrated circuits are normally what? U. So this is the diagram that we'll be looking at a little bit. This comes in the textbook. Now I don't know about what they do in the I might run those off and give it to you. So let me get through with this real quick. We need to go over this lab. Oops, that's the data sheet. I'm listening. No, you can't say normally. Can't say normally. Because it's got two inputs. They're not normally. If they were normally something, I wouldn't use an AND gate, right? You understand? An AND gate says all highs get a high. I've got 4 combinations I could put on this, which is normal. None of them's normal. I got 4 I can put there, right? You understand? Yes or no? That would be like saying you normally park in the same parking space no matter where you go. Right? You understand? It's a 2 input AND gate, and I can put 4 different combinations on that input. Only one of them would give me a high. There is no normal input on an AND gate, right? Now there might be a normal input in a circuit, right? You understand, where it's designed in a circuit, but you've got 4 combinations you can put in there. It's just like me putting 4 parking lot spaces out there and say, you can park in any one of them you want to, right? You understand? What do you mean all 4 of them? But that's not a normal input. That's just one of the 4 inputs that we could put in there. You're okay, but you're not listening to what I'm saying. You're saying what input is normal, and I said there is no normal input. One of those inputs would give me a high. So if I have an 8 input AND gate, it's going to take all highs to get a high. But I've got 255 other combinations that would give me a low. Understand what I'm saying? So which one of those would be normal? What would be normal? If I've got 256 combinations I could put on an input, which one would be normal? None of them. It depends on, now there might be a normal input inside a circuit, right? You understand what I'm saying? But it don't mean, like if I put 4 parking spaces out there, you might normally park in one. Right? You understand? But that don't mean that's normal, because you got a choice of what? Of 4, right? It's just like when you pull in out here, you got a choice of and how many combinations would there be out here in this parking lot? So you bring in 16 people, right? You understand? Or you bring in 4 people, 4 cars, and each one of them's got their own option, right? Does that make sense now, Jason? Then OR gate. Then this is where we're going to bring a clock input in. And where we're going to get our clock input at? Huh? No, an oscilloscope is like a meter. We don't get signals from the oscilloscope like we don't get voltage from our meter, right? An oscilloscope is a tool that we measure with. So I've seen people do this. They say, I need a 10 kilohertz sine wave, and they'll come over here and be screwing around with their scope. And they say, I can't get 10 kilohertz because they're trying to get the oscilloscope don't generate the waveform. The oscilloscope measures the waveforms that's there. Okay. So where we're going to get our clock input at? Not from the oscilloscope. We're going to use the oscilloscope to measure it, but we're not going to get it from there. Huh? Yeah, but we got this guy right here. This is a TTL clock right there. Okay? You understand that? Yes or no? Now the problem is that it says I need a 10 kilohertz clock, right? You understand that? And all I've got this coarse adjustment up here that I put on 10 kilohertz, and then I've got this fine adjustment right here. So how do we calculate? And my scope don't measure frequency. It measures what? This scope will measure frequency, but we don't get used to using that. So how do I calculate time if I know frequency? It's the reciprocal of frequency. So it says I want a 10 kilohertz sine wave, or 10 kilohertz. I get used to teaching AC. A digital clock. 1/10 kilohertz would give us what for the period? Y'all got calculators? That's what I like. I said give us watt for the period. 100 microseconds, good. So what do we want to set our scope on? We're not going to set it on 100 microseconds because that'd be trying to put 100 microseconds inside one division, right? You understand that? So I have mine. Can y'all see what I have mine set on? I have it set on 10 microseconds. So how many divisions do I want? 10, you know. Oops, wrong channel. Still wrong channel. So if I reference it to this guy right here, then I'm going to look for that other one. So what does that mean? That means I've got it spread out too far, right? That makes sense? So I'm going to come up here and take a fine adjust. If it starts moving. Oh, here's fine adjust. And we need to make it smaller, right? What do you mean? I'm doing the fine adjust on this guy right here. So my scope is set up. I've got it set on 10 microseconds per division. So I'm trying to get 10 divisions. Okay. That makes sense? Okay. And so what I did is I set my course adjust on, oops. I set my course to adjust on 10 kilohertz. And then I started adjusting the fine adjust, which is this guy right here, until I got 10 divisions. So there's 10 divisions. Now what we're going to do is we're going to put this on one input of our gate. I think we're going to start off with the AND gate. I need to have this set up 1 volt per division. This guy doesn't put out a square wave. It puts out, looks like that's 10 divisions, 1, 2, 3, 4, 5, 6, about a 60% duty cycle. So what is the duty cycle? Or fall to fall. We're doing fall to fall. But it's the percent of the period that the signal is high. So this one's real easy because we got 10 divisions. So I come over and I count 1, 2, 3, 4, 5, 6. So that means it's high 6/10 of the time, right? You understand, of 60%. Are we okay? Now what we're going to do, of course, is we're going to put this on the one input of the gate. Let me find the lab. Yeah. So this is an OR gate. We got one input connected low. So every time this goes high, the output should go high. So this should follow the clock, right? Everybody understand? Yes or no? Huh? Yeah. That's what that is right here, right? We okay? is on the clock, on whichever OR gate you choose. Now we'll look a little bit at this is a TTL gate. So right now when we come over here and, oops, wrong thing, Rich. Okay, so what it will tell us to do, replace pin A, previous circuit, 10 kilohertz square wave, display the input waveform on the oscilloscope, waveform on the oscilloscope, do not trigger, see, but trigger. Now, set the B input high. What I recommend you do, guys, is just leave this guy, just connect this up to one of your switches. So I need to come back and correct that, because here we're going to connect the B input low. Down here we're going to connect the B input what? High. So here when the B input is low, then anytime the clock goes high, the output will go high. Here, if the B input is high, what should we expect? So that means here the output is going to follow the A input, right? You understand? So what's going to happen down here? So what does this gate say? This says any high gives me a what? High. So what should we expect? If I connect the B input high and put a clock input on the A input, what should we expect the output to do? It's going to be high all the time, and this is what they're showing you about enable and disable, right? You understand? So what's that? The A input, not the Y input, the A input. So what they're doing is they're not drawing the B input. This is actually the A input, and that needs to be clarified too. So this is the A input. No, I mean, it's understood to be whatever you say, because all they're really doing is saying what's going on with the Y. And this is what we're trying to do, is showing how we can use that other input as an enable and a disable. Okay, guys, and there's the questions. You're about to draw some waveforms, kind of like we did in class one day. They will give you the A, B inputs, and you got to figure out what the X output would be. So let's go ahead and go to lab. Any questions on this?